In this video, we're going to walk through an acid-base titration experiment and calculate the pH of the solution being titrated. We'll start with a beaker with 25 milliliters of 0.1 molar HCl, and we will titrate that with a 0.1 molar NaOH solution here in the burette. Now we're going to go through a series of calculations where we calculate the millimoles of hydroxide, millimoles of hydronium, concentration of hydronium, and ultimately the pH after we do 4 different kind of titration steps. We'll add first 10, then 25, then 35, then 50 milliliters of the sodium hydroxide solution from the burette to the beaker, and we'll calculate the pH as a result. Let's start with the beaker before we add any of the sodium hydroxide solution. This is our 25 milliliters of 0.1 molar HCl solution. It has approximately 0 moles of hydroxide. The concentration of the millimoles of hydronium would be 25 milliliters times the molarity, which would give us a 2.5 millimole. The volume is 25 total, so 2.5 millimole divided by 25 gives a concentration of 0.1 molar, giving a pH of 1. Next, let's calculate the pH after we add 10 milliliters of the 0.1 molar sodium hydroxide solution to the 25 milliliters of HCl. Let's go through the calculations again for the millimoles of hydroxide, hydronium, overall hydronium concentration, and then pH. We just added 10 milliliters of 0.1 molar sodium hydroxide solution. So that's 1 millimole of sodium hydroxide. When the hydroxide is added, it reacts directly with the hydronium. So to calculate the hydronium concentration, we originally had 2.5, but now we're going to react away 1 millimole worth of that. So now we have 1.5 millimole hydronium left. The total volume is now 35 milliliters because we've added 10 milliliters of the sodium hydroxide solution. So the hydronium concentration is 1.5 millimole divided by 35 milliliters, which gives a concentration of 0.04 molar. The pH of that solution is 1.37. Let's calculate the concentration after we add another 25 milliliters of sodium hydroxide. First, just note that we will add equal volumes of equal molarity sodium hydroxide and HCl, so the number of moles or number of millimoles of hydroxide will be equal to the number of millimoles of hydronium, so the pH will be neutral, with a concentration of hydronium of 1 times 10 to the negative 7th. Next, let's calculate the concentration once we've added 35 milliliters of the sodium hydroxide solution to the beaker. Now let's calculate the concentration of the millimoles of hydroxide, millimoles of hydronium, final hydronium concentration, and the pH. We've added 35 milliliters of 0.1 molar sodium hydroxide solution. Therefore, we've added a total of 3.5 millimoles of hydroxide. We originally had 2.5 millimoles of hydronium. We've added 3.5 of hydroxide. Therefore, we have an extra 1 millimole of hydroxide remaining. This 1 millimole of hydroxide is in 60 milliliters. You can calculate the pOH, which is 1.76, or the pH is 12.22. In the final step, we're going to add 50 milliliters of sodium hydroxide solution to the beaker. After adding 50 milliliters, we will have added a total of 5 millimoles worth of hydroxide to the beaker. We originally had 2.5 millimoles of hydronium, so subtracting that away, we get 2.5 millimoles of hydroxide remaining. That's in a total of 75 milliliters for a concentration of 0.03 molar. So that's a pOH of 1.48 and a pH of 12.52. Now that we're done calculating the pH through our titration experiment, let's go back and graph the pH in the beaker as a function of the volume of the sodium hydroxide solution added. I have 5 scenarios here. I'm going to label them as A, B, C, D, and E so that I can label the points on the graph. Let's start out with scenario A, where we've added no sodium hydroxide solution, so a volume of 0. There we calculated the pH to be 1. After we added 10 milliliters of sodium hydroxide, we calculated the pH to be 1.37. After we added 25 milliliters, we calculated the pH to be 7. Then after 35, the pH was 12. And after 50, the pH was 12.52. If you made more measurements throughout the course of the experiment, you would get a titration curve that looks like this. Let's look at 3 different titration curves. In the first titration curve, we're going to titrate a strong acid with a strong base. In the second titration curve, we're going to titrate a weak acid with a strong base. And in the third titration curve, we're going to titrate a weak base with a strong acid. The example we did in the previous slide was a strong acid being titrated by a strong base. This curve will look identical. Notice that on this titration curve, the pH starts out very low because we have a strong acid. The pH then rises as we add more and more strong base to the solution, and eventually it plateaus at a high pH. There's a point along this curve where the number of moles of acid is equal to the number of moles base added, and that's called the equivalence point. When you titrate a weak acid with a strong base, you start the titration at a slightly higher pH because it's a weak acid. The titration curve then plateaus in this region here called the buffer region, where you have appreciable amounts of the acid and its conjugate base. The pH then rises here. We reach the equivalence point, and then the pH plateaus out. Notice that because we're titrating a weak acid with a strong base, when we add equal molar amounts of the acid and the base, the pH of the solution is more basic. In the final example, we're titrating a weak base with a strong acid. Here, the titration curve will start out basic, pass through a buffer region, and then the pH will drop dramatically as you add more of the strong acid until it eventually turns over and plateaus at a very acidic pH. Here, at the equivalence point, when we have equal amounts of acid and base present, the final solution is slightly acidic because we are titrating a weak base with a strong acid. So the salt solution of those two ends up being slightly acidic.